Location, geologic and tectonic setting. The study area, Fig.1, Niger Delta, is situated in the Gulf of Guinea. From the Eocene to the present, the delta has prograded southwestward, forming depot belts that represent the most active portion of the delta at each stage or its development. The ideas expressed on location, geologic and tectonic setting is from. The depot belts in this basin form one of the largest regressive deltas in the world with an area of some 300,000 square kilometers, sediment volume of 500,000 cubic kilometers and a sediment thickness of over 10 kilometers in the basin depot center. The onshore portion of the Niger Delta Province is delineated by the geology of southern Nigeria and southwestern Cameroon. The northern boundary is the Benin flank, an east-northeast trending hinge line south of the West Africa Basement Massif. The northeastern boundary is defined by outcrops of the Cretaceous on the Abakaliki High and further east-southeast by the Calabar flank, a hinge line bordering the adjacent Precambrian. The offshore boundary of the province is defined by the Cameroon volcanic line to the east, the eastern boundary of the Dahomey Basin, the easternmost West African transformed fault passive margin, to the west. The Niger Delta Province contains only one identified petroleum system. This system is referred to as the Tertiary Niger Delta, Akata-Abata, petroleum system. The maximum extent of the petroleum system coincides with the boundaries of the province. Most of the petroleum is in the fields that are onshore or on the continental shelf in waters less than 200 meters deep and occurs primarily in large, relatively simple structures. The tertiary section of the Niger Delta is divided into three formations, Fig.2, representing prograding depositional facies that are distinguished mostly on the basis of sand-shale ratio. The type sections of these formations are described by and. The Akata Formation at the base of the delta is of marine origin and is composed of thick shale sequences, potential source rock, turbidite sand, potential reservoirs in deep water, and minor amounts of clay and silt. Beginning from the Paleocene and through the recent, the Akata Formation formed during low stands when terrestrial organic matter and clays were transported to deep water areas characterized by low energy conditions and oxygen deficiency. Turbidity currents likely deposited deep sea fen sands within the upper Akata Formation during development of the delta. Deposition of the overlying Abata Formation, the major petroleum-bearing unit, began in the Eocene and continues into the recent. The formation consists of paralic siliciclastics over 3,700 meters thick and represents the actual deltaic portion of the sequence. The clastics accumulated in delta front, delta topset and fluvio-deltaic environments. In the lower Abata Formation, shale and sandstone beds were deposited in equal proportions, but the upper portion is mostly sand with only minor shale interbeds. The Abata Formation is overlain by the third formation, the Benin Formation, a continental latest Eocene to recent deposit of alluvial and upper coastal plain sands that are up to 2,000 meters thick. The tectonic framework of the continental margin along the west coast of equatorial Africa is controlled by Cretaceous fractures zones expressed as trenches and ridges in the deep Atlantic. The trough represents a failed arm of a rift triple junction associated with the opening of the South Atlantic. In the delta, rifting diminished altogether in the late Cretaceous. After rifting ceased, gravity tectonics became the primary deformational process. Shale mobility-induced internal deformation occurred in response to two processes. First, shale dye piers formed from loading of poorly compacted, overpressured pro-delta and delta slope clays, Akata Formation, by the higher density delta front sand, Abata Formation. For any given depot belt, gravity tectonics were completed before deposition of the Benin Formation and are expressed in complex structures, including shale dye piers, rollover anticlines, collapsed growth fault crests, Fig.3, back-to-back features and steeply dipping closed-spaced flank faults. Deposition of the three formations occurred in each of the five offlapping siliciclastic sedimentation cycle that comprises the Niger Delta. The cycles, depot belts, are defined by sedimentary faulting that occurred in response to variable rates of subsidence and sediment supply. The interplay of subsidence and supply rates resulted in deposition of discrete depot belts. When further crustal subsidence of the basin could no longer be accommodated, the focus of sediment deposition shifted seaward, forming a new depot belt. Each depot belt is a separate unit that corresponds to a break in regional dip of the delta and is bounded landward by growth faults and seaward by large counter-regional faults or the growth fault of the next seaward belt. 5 major depot belts are generally recognized, each with its own sedimentation, deformation, and petroleum history. The Northern Delta Province, which overlays relatively shallow basement, has the oldest growth faults that are generally rotational, evenly spaced with increased steepness seaward. The Central Delta Province has depot belts with well-defined structures such as successively deeper roll-over crests that shift seaward for any given growth fault. Lastly, the Distal Delta Province is the most structurally complex due to internal gravity tectonics in the modern continental slope. Generalized geological map of Niger Delta Basin. Schematic dip section of the Niger Delta. Principal types of oil-field structures in the Niger Delta with schematic indications of common trapping configurations, after Tuttle et al., 1999.